Okay, good morning. So today the last paragraph of this part, of this first part of the class on the Dimer model, phases of the model. So probably the highlight of this part, if not of the class. Okay, so phases of the model. It means, so it's always the same setting, right, in this paragraph. So I have, let's say, G, or let's say G1, which is a weighted graph in the torus. And this gives me, so this is bipartite, of course. And so now this gives me a bipartite biperiodic weighted graph. So in biperiodic, it's invariant under the action. It's just that I want to write lambda for this lattice. Okay, now the question is, how does the model change when you vary parameters? Okay. You vary the parameters. And of course, the question then is which parameters? Okay. So remember, since it's a bipartite graph, let's say this one, we saw that the right parameters are not the edge weights. Remember, there is another more sensible way to do so. So which parameters So to answer this question, I need to make a very small paragraph about so-called magnetic field coordinates. So let's recall our setting. Let's say recall, this is something we did at the very beginning of this paragraph. Recall that the right, so we have G1, which is in the torus, and therefore the right parameters to consider are the following ones. The right are the f plus 1 following ones. F is the number of faces. So if you set beta E equal to, so I had not put this notation, but it's okay. If E is oriented from white to black, -1 in the other way, it's the other way around, then the right parameters to consider are QF, which is by definition the product nu E beta E for E in the boundary of F. Remember, these were these alternating products. And this is for every F in the set of faces of G1. But we have the fact that the product of all of these is 1. So actually you have F minus 1 of them. Okay, and then you have two more to consider, which are given by the homology of the torus. So Qi equal how do I want to write this? Let's say alpha I, and this will be for I equal xy. So overall, I have f minus 1 plus 2, that is f plus 1 parameters. And let me just recall how this goes. So remember, you have these two So that's the boundary of the fundamental domain. And the way I want to define so I need to have two alpha x, alpha y, two cycles, two oriented cycles in the graph that induce a basis of the homology. And for all the signs to work fine, I want to put them in the following way. So I want alpha x to be like this. It will be alpha x, and alpha y like this. Okay. So you remember this? These were things we did. Okay? Something weird? So these are two oriented cycles that lie on the graph. Okay? To have all the weights, you needed to have the boundary of all the faces, and on top of that, you needed one cycle for any element in the basis of the homology. Okay? And here I could have chosen my alpha x, alpha y in any way that they generate the homology, but for everything to work in the right way, I chose them like this. Okay. Okay. Now let us write, instead of mu of E, I will write this as the exponential of minus the energy of the edge. That's just another way to parameterize these edge weights. So these are, you know this, that these are these Boltzmann weights. It's the energy. So if you put all of this together, it means that gauge equivalence classes of energy weights, of energy parameters, are parameterized by, so now we have f minus 1 plus 2 real numbers, so I will write this as bx, by, bz, which belong to R2 plus Rf minus 1, where, for example, Bx will be given by, so if I put everything together, it will be the sum for all edges in alpha x of minus Be and okay, so I just did two things. One is this that we already had done. So it's to say, okay, if you want parameters up to gauge equivalence, then you should not look at the edge weights, you should look at these new weights. And then I just parameterize them rather by the energy than by the exponential minus the energy. Okay. Okay, so these are called, these coordinates, these are called the magnetic field coordinates. And now what we will do, for reasons that will become clear, I think, very quickly, is that we will keep Bz fixed, and we're going to vary Bx and By. Okay? So this is what we're going to do. So we're going to have the phases of the model, the phase diagram is going to be something in R2. Okay? It's going to depend on these two parameters here. Okay. what we do, we keep BZ fixed. So if you prefer, it means we keep all of these here fixed, and we vary Bx, By in R2. So now we need to understand how this is done in terms of edge weights, because we've done everything in terms of edge weights. So let's understand this. So in terms of edge weights, passing from some fixed Bx, By, Bz to Bx plus delta Bx, By plus delta By, and not changing Bz, is done as follows. So let me continue on this board. So you have to multiply the edges in some way, the edge weights, and I'm going to explain it here. So the way it goes is you have to multiply, so now I really have to copy my notes. So white, black, this one, you multiply this edge weight, the edge weight, by e to the power delta Bx. This one you multiply by e to the power minus delta Bx. This one you multiply by e delta By, and this one by e minus delta By. Okay, you just check. Unfortunately, I just erased the drawing that enabled us to check it, but you can check that it works this way. Okay. So I just need now a notation for the new measure where I have magnetically altered the parameters. So for a fixed G1 nu, we write nu1 and then mu n for the corresponding measures. And let us write then mu n tilde Bx By for the measures on Gn, for the measure on Gn. So for the magnetically altered meaning we did this, okay, with Bx and By, okay? Okay, so it means we fix the edge weight nu, this corresponds to bx, by equal to, this corresponds to here, these parameters 0. So I'm sorry, this is not very clear. I might have some parameter here that I will have a parameter here that will not be 0. But then we fix this as the origin, and then this means that we took the measure mu n and I have altered it by bx and by. Okay, so if you wish, maybe I took the notations of the paper, but maybe a delta here might have been a little bit better, you see? So this is actually, these parameters here, they are by how much we alter the basic measure. Okay, the fixed measure we have at the beginning. Okay? Is this clear? So again, we fix nu, and then we alter, and then we look at how the measure changes when I alter it, like multiplying this by e minus bx, e bx, etc. Okay. Good. So, first set of results, Röntgen function and free energy. So the first natural thing to look at is how does the free energy change when you vary these parameters, these magnetic field coordinates. Okay. So I need to introduce a new object. I could have done this in the last class. It's really an object in real algebraic geometry. So given a polynomial p its Röntgen function is the function f from R2 to R defined by, so f of x, y is equal to that's the definition. So of course now it comes a little bit as falling from the sky, but it is an object that is natural in the setting of real algebraic geometry. Notice that, so note that this integral, the integral is singular if and only if there exists ZW in the torus such that EX, Z, EY, W lies in the curve. And this we had seen, this is equivalent as asking that XY is in the amoeba. So this is clear. Now let me give you two facts about Röntgen function. So f is a convex function which is strictly convex over the interior of the amoeba and affine over each component of the complement. Moreover, if P describes a Harnack curve, then remember in this case, the components of the complement correspond to the integral points of the Newton polygon. This is something that we had seen. So if P is a Hanna curve, then each point, so each component of R2, this corresponds to a point in, so an integral point in the Newton polygon. And I don't know if you see it coming. The fact is that this integral point will be equal to the gradient of f on this component, right? So it's an affine, so f is affine over this, component, and its gradient is given by the corresponding integral point here. So this is the gradient of f over, over this component. Let me give you an example. So let's take PZW equal 5 plus Z inverse plus W inverse. And okay, so let me draw again the Newton polygon. Okay, this is N of P. And then we know that the amoeba has, since it's a Hanna curve, we know that we have, we have one tentacle. So let me draw the amoeba again. We drew it already. Right? So we have one tentacle for each side here. And you see we indeed have one component in the complement for each integral point of the Newton polygon, right? And now let's look at these points. This is -1. So here it means that, so the function, the Röntgen function, the point is the Röntgen function, you can basically sketch it quite precisely just by looking at this thing, right? We know that it's going to be, so just looking at this thing, I can sketch already the amoeba. And then here I know that the gradient of f here is going to be -1, 0. And the gradient here is going to be 1, 0. The gradient here is going to be 0, 1. The gradient here, 0, -1. And here, 0, 0. It's going to be flat right here. You see, and it's going to be strictly convex on the rest, so I can try to draw the graph of the function. Something like that, right? You see the gradient here, -1, 0, 1, 0, 0, 1. Well, you see. Okay. And now I will keep this. But now let's look at this, this thing here. This is the way I change the weights when I want to pass from the basic model to the magnetically altered one, so I have to multiply by E minus Bx, etc. So this should ring a bell. So this is exactly the way we constructed the characteristic polynomial, right? Multiplying by z this one, and by z inverse this one, by w inverse, right? So this means that, note that really by construction, or I don't know by construction, I mean by this drawing here, and by definition of the characteristic polynomial, the characteristic polynomial, let me write it P tilde of ZW for, so for mu1 tilde Bx By is obtained from PZW, which is the one for mu1, by P tilde ZW is equal to P EBX Z E BYW. Right? This is simply this drawing that I have here and the definition of the characteristic polynomial. There's nothing more. Hence, the free energy of the model with magnetically altered weights Bx, By, hence, the free energy, so I'm not gonna define the notations, but you will understand. So it's Z with these magnetically altered weights is given by what? So we know by the theorem that we proved last time. This is 1 over 2 pi I square integral over t squared P tilde ZW, log right? That's the theorem we proved. And so you see that this is exactly the Ronkin function of Bx, By. The way the free energy changes when you vary these well-chosen parameters is given by the Ronkin function of the characteristic for P ZW. This is not even stated as a theorem in Kenyon of Sheffield, but to me this is already completely amazing. That you see, it means that, for example, you take the square octagon graph and you put all the weights equal to 1. The characteristic polynomial is this one. And so so this graph actually tells you how the free energy, it tells you the value of the free energy when you change these weights, magnetically altered weights. And again, to do this, of course, if I want to have the precise number, then I have to compute. But otherwise, if I just want to understand the behavior, I have everything completely for free just by knowing these general facts about Ronkin function. For example, I know without any computation, without anything, that if I take the square octagon graph, lattice, and I change the weights like this with Bx and By sufficiently small, then my free energy here will not change. right? Because here we're flat. It's constant. It's locally constant here. So, and this is of course just one example, but then you know that it's strictly convex on the amoeba. You know that if you're on this component here, then it's going to move in this direction. If you change this direction here, then you're not going to move, etc., etc. So this is already quite amazing. I mean, if you think about, so what does it mean to solve a model? Here you see that, okay, it's solved in a very, very deep and precise way. You have an explicit description of how the free energy is changing when you change these two parameters, for example. Okay. Good. So, okay, why is this related to the phases of the model? Because intuitively, I don't know if you have this, if this intuition is correct for you, intuitively, one thinks that the places where the free energy is not smooth are the places of phase transition, right? So now the places where the free energy is not smooth. So here, where are these places? So you see these places are at the boundary of the amoeba, right? i.e., for us, it's the boundary of the amoeba. And so it's funny, it corresponds to the image by the amoeba map of the real part of the spectral curve. But anyway, so the boundary of the amoeba should correspond to some phase transition. So can we make this precise? So to make this precise, we need some more definition. So we need the notion of ergodic Gibbs measure. So why do we need this? So okay, to make the notion of, well, if you want to make the notion of phase transition precise, then you need to be working in infinite volume, right? So far, we always looked at measures on a finite, probability measures on a finite graph, right? But now we're going to have to work with the full biperiodic graph, and for this you need this notion of Gibbs measure. So far, we worked on, let's say, Gn mu torus, which is a finite graph. And then, so the measure is easy to define. We just took the product of the weights, and then we divided by, this is completely fine. So now we need to work over the infinite biperiodic graph. G R2. So how to define a measure there? How to define a measure on the infinite set of perfect matchings on G. So I'm simply going to introduce some terminology, and it's not. I even hesitate to introduce it, but okay, so let's do it. So I think you've seen this, well, these kind of things in some other classes, but let's say a Gibbs measure so here for me it would be a Gibbs measure on this set. So is a probability measure mu such that. Okay, so let me maybe do a little drawing. So let me take G prime, which is finite. So for any finite G prime in G, for any M0 perfect matching on G but G prime. So you see I fix a perfect matching on the infinite part, and for any perfect matching on G, we have the measure of M restricted to G prime, conditioned on. So we're only looking at the perfect matchings that coincide with M0 outside. So M restricted to G, but G prime is equal to M0. This should be given by nu of M restricted to G prime over Z G prime nu. You probably know these things better than I do. These are the so-called DLR conditions, right? You know this? You've seen this probably in the class of Yvan. Okay. But you see, so that's the very natural condition to state, right? You fix everything except on a finite subgraph, and on this finite subgraph, you want it to behave the way it should here. Okay. That's the Gibbs measure. And what does it mean that this Gibbs measure is ergodic? So a Gibbs measure nu on M of G is ergodic if it is invariant under the action of lambda, which is again this lattice, right? And ergodic with respect to this action, this means all invariant subsets, so all lambda invariant subsets have measure 0 or 1. Okay, and now here are the facts. The only facts I will need, really, I could have not defined this, it would have been fine. So these facts are due to Sheffield. He proved them in his PhD thesis, that was in 2003. The measures mu n converge to an ergodic Gibbs measure we're going to denote this by EGM. So this is not the hard part of his theorem, but actually I will quote the hard part in parentheses because we're not really going to use it, but it's worth being quoted. And actually all ergodic Gibbs measures on, well, G are classified by what is called their slope. And again, I'm not going to define this, but just for general culture. All ergodic Gibbs measures are classified by the slope and can be obtained by taking such kind of limits. This is a little bit difficult to understand as such, but it just means that here I took the full measure mu n on all the perfect matchings. And actually what you can do, you can define the slope of a perfect matching, and then you just look at the measures here restricted to the subset of perfect matching with some given slope, and this will converge to a Gibbs measure of the given slope. And all the Gibbs measures, all the ergodic Gibbs measures are given in this way. So this is what I meant by such kind of limits. It's not exactly this limit. Okay, so of course we can do the same for the magnetically altered ones. So let us write mu tilde of bx by for the limit of these mu n bx by. And now I can phrase the question in a more precise way. How do the ergodic Gibbs measures mu tilde bx by change or vary with bx by? You see, again, what is the point of having these measures in infinite volume? Well, here now we can really talk about things like exponential decay of correlations and things like this. And this is exactly what's going to happen. So there's going to be 3 different type of phases, and maybe you can guess what it corresponds to in terms of bx by. Of course, it's going to be related to the amoeba. I think it's a good time to make a break, and we'll resume in 15 minutes, and I'm going to state the theorem and give some ideas of the proof. Of course, not the whole proof, but we actually saw most of the tools that are needed, so I can give you good ideas of the proof, and then this will be it for the first part of the class. Okay, so now I can really come to the phases of the model. So I want to work also with high functions. So remember how it works? When you need a fixed unit flow in order to have to each perfect matching to have a height function. So I will fix an element of mg1, hence defining some aperiodic M0 perfect matching on G, which induces, as we saw, an injective map from the set of perfect matchings to the set of height functions, so functions like this. Okay, and okay, I wanted to fix also the value of h on a function on a face, but what we're going to do is only consider difference of height functions. So it's not we don't need to fix a value on a face. That's fine. Okay, so here's the definition. Yeah, so maybe just say here. So it means that hence an ergodic Gibbs measure mu on n of G defines a measure on height functions. Okay, so let's define the three phases. An ergodic Gibbs measure mu is a frozen phase if so if there exists faces f prime arbitrarily far apart such that h of f minus h of f prime is deterministic. Okay, the first, then one thinks, okay, is this actually possible? Of course it's possible. So for example, you just take mu to be the delta measure on M0. But if you take this, it means that you're going to have a single perfect matching with probability, positive probability, it's M0 itself. And then if you take the corresponding height functions, it's just going to be constant. And okay, so therefore this thing is always 0. Okay. So that's just kind of a very degenerate example, but just so you see that it exists. Okay. Now, a non-frozen ergodic Gibbs measure mu is a gaseous phase if the mu variance of this difference is bounded. Independently of f prime. And finally, a non-frozen ergodic Gibbs measure mu is a liquid phase if the mu variance here is unbounded. Okay. So of course this covers all the possible cases, right? So first you say either you're frozen or non-frozen. If you're frozen, okay, you're frozen. If you're non-frozen, then you have this dichotomy. Okay, so you have three phases. And here's the theorem. So the main theorem of this paper by Kenyon, Okunk of Sheffield The ergodic Gibbs measure mu tilde of Bx By is a frozen phase, is a frozen, respectively, liquid, respectively gaseous phase, if and only if Bx By so lies in the closure of an unbounded component of the complement of the amoeba, respectively in the interior of the amoeba, respectively in the complement, in the closure of a bounded component of the exterior of the amoeba. So there are three phases. There are three possible positions of a point with respect to an amoeba. You can be in the amoeba, you can be in an unbounded component of the complement, you can be in the bounded component of the complement. These correspond to the three phases. Moreover, so what we had called edge-edge correlations, you remember, decay exponentially fast, exponentially in the gaseous phase, decay polynomially in the liquid phase, while some of these correlations do not decay at all in the frozen phase. In the frozen phase. Quite amazing, isn't it? So there are all kinds of results you can prove in statistical physics, but if you're interested into exact results, I don't think it gets much better than this. Right? More explicit than this you cannot get. Right? So let me just give some, I always have these running examples, so let us look at them together. Okay, so let's consider first the hexagonal lattice with all the weights equal to 1. Then we know, right, so P ZW is 1 plus Z plus W. So we have this Newton polygon. So the corresponding amoeba something like that. So in this case, we have only two phases that are present. So we are frozen outside. and liquid inside. And again, to draw this, I didn't need anything. I just needed this. I just needed to compute this. And remember how easy it was to compute it. You just take the Castellan matrix, you put ZW, and you're done. Maybe let us just look together at, just have a slight intuition of what's going on. For example, why would it be frozen if Bx becomes very big? Let's at least try to understand this. So I might not do correctly the black and whites here. Let me not be so precise, but it's not so important here. So let's say that this was gamma x. No, let's say gamma x, gamma y. And so we start with weight 1 everywhere. So we're in the middle. We're right here. And OK, it turns out in this case, we are in the liquid part. So if we look at the model, if we look at the homogeneous model on the hexagonal lattice, well, it means that we are in the liquid phase. So it means that the mu variants are unbounded and the edge correlations decay polynomially. OK, so we know this. Now, let's alter this weight. So what I'm going to do is I want Bx to become big. So let me fix this edge here. And I'm going to multiply it by EBx. And now I take Bx to be big. What will happen? So you take Bx big, it means this thing will grow huge compared to the other ones. So it means that actually, as Bx grows big, we are tending, mu grows towards, well, this delta measure on M0, where M0 would be the perfect matching given by this one edge, right? So you agree that at some point it's natural that if we grow Bx really big, we should be frozen at some point. Okay. Of course, the same with By. Okay. Second example, square lattice. So this is not so interesting because, again, you only have these two behaviors, but let me draw it anyway. So in this case, we're like this. And inside, so here there is a singularity, but it doesn't matter. We're still in the liquid phase. So here we're liquid, and outside we're frozen. And I think the simplest example that exhibits the three phases is the square octagon one. That is, in this case, as we saw, the amoeba looks something like that. And in this case, again, I am liquid phase inside the amoeba. Then I'm frozen outside. So far, it's the same thing. And I have this gaseous phase here. So it turns out if I take my square octagon lattice with weights equal to 1, then I'm in a gaseous phase. And then if I play the same trick as here, and I want to increase the weights of, let's say, these, two vertical edges that is crossing the boundary of the finite domain, and I multiply by EBx this one, by E minus Bx this one, then I will first pass through a liquid phase, and then I'm going to be frozen. in a nutshell, you have everything you want to know about the model is just contained in this one polynomial. This is really the amazing thing. And what is really incredible is this fact that each time you have a significant object in real algebraic geometry, it corresponds to a significant object in the Dimer theory. So, for example, the Ronkin function, free energy, amoeba, phase diagram, etc. Okay. So what I want to do in the half hour that is left now is to give you some idea of the proof. We'll see a little bit how it goes and how much I will give you, but some ideas, and in any case, I will stop this part on the Dimer model at the end of this half hour. Okay, so the starting point of the proof is a tool that we developed a long time ago, and I really wanted to write this statement clearly 1 or 2 months ago because I knew we would use it now. So it's the fact that, first tool, it's the expression for these edge-edge correlations in terms of Castelline matrices in the case of the torus, because we're working on the torus. So as we saw, so that was in the paragraph, 1.2. We have the following result. If I want to consider the edges, so E1 given by W1, B1, EK, WK, BK, then the corresponding edge-edge correlations, let's write it for mu n. This will begin by what? So first you need the product of the coefficients of the matrix. And then you have 1/2, and you have 4 terms. I'm not going to write again these 4 terms. They were a little bit complicated. But let me write maybe the first 2 of them. So it was, I think I used the following notations. Simply, we didn't have the n here. And determinant of K 0, 0, n inverse BI Wj. And then you had plus Z 1, 0, n, Zn, etc. Okay, I'm not writing, so we had 4 terms. We had an alternating sum. We had 1 minus sign, and the other 3 were pluses. And we had 0, 0, and then you have the other 3 terms with 1, 0, 0, 1, and 1, 1. Okay, I'm not writing everything. Okay. Now, what we want to understand is the limit of this object when n goes to infinity, because this will be exactly the edge-edge correlations for mu. Okay? We want to understand the corresponding edge correlation for mu, the limit of this un, that is the limit of. So we have to understand the asymptotics of these things here. Okay. Right. Now, so that's the first tool. The second tool is, remember that now we have these kns. So we were able to write the kns in terms of the k1. Remember, when we kind of block diagonalized things for the free energy stuff? Here we need to do a same kind of trick, but for the kn minus 1 this time. So this is the first tool. So we were able to express, let's say, kn in terms of k. now, so it is possible to do the same for kn theta tau minus 1. Now this is a little bit more complicated. So of course I'm not giving details. They're not giving details either, actually. So they're referring a lot to an earlier paper of Kohn, Kenyon, Prop, where they do everything in full detail for the square lattice and basically just say, okay, once you know that the curve is Harnack, then everything works fine. So of course I will not give you detail, but I'm going to give you the formula, which is a little bit complicated. So kn theta tau inverse. And now, so here I need two, so a black and a white vertex. So what I'm going to do, I'm going to write a general pair of black and white vertices. I'm going to write them as BW plus XY, where B and W lie in the same fundamental domain. And XY is something in Z square that expresses the difference between them. Okay? So here maybe I'll just write this. So we have BW that lie in the same fundamental domain. And XY is in Z2. So you agree, we can always express two, a black and a white vertex, we can always express them in the unique way like this. Okay. Right. So what they prove is that this is equal to 1 over n squared, sum Zn equal minus 1 theta, sum Wn equal minus 1 tau, and then Q BW ZW over P ZW ZX WY, and that's it. Okay. With what? So this is explained, the XW they're explained. So I'm sorry, XY, I'm sorry, there are two W's, but I hope they're clear. One is a complex variable, the other one is a vertex. It should not be too bad. So I just need to explain to you what is this thing here. So basically it plays strictly no role in the rest, but so where, actually if you look at KZW, the inverse matrix, and you look at the BW part, this is the one for the 1-by-1 domain. So here it makes sense to look at BW that lie in the same fundamental domain, right? So I look at the inverse, so I look at the matrix with DW, I look at its inverse, and I look at the coefficient which correspond to BW. So this is equal to, this defines this. Okay, so this is some polynomial that will play no role. There are a finite number of them. It just depends on B and W in this fundamental domain, and that's it. Okay. Right, so now of course you see that this is a Riemann sum for some integral. So this is a Riemann sum for an integral that I will denote. So this is now really a notation. Integral over t square. So Q sorry, let's write this. Okay. Now note that this thing here is nothing but the xy Fourier coefficient of this thing here, that is this, of k minus 1 zw Okay. So of course then you have some kind of convergence issues, but basically the analysis is very much the same as the one we did for free energy, right? We had this kind of situation for the free energy. We had the fact that, okay, the partition function was not exactly the same as these k's. It was also an alternating sum, but that was the first part of the proof. We saw it's okay. Basically, when you look at the limit, you can actually compute everything just from these evaluations of P. Okay. And then second part, but okay, does our Riemann sum converge to the actual integral? That was the second point that was not so easy. And here it's the same kind of analysis that tells you actually it's completely fine because our curve doesn't meet the torus too much, etc. We have convergence of this to the Riemann sum. And then these four terms, they will give, well, they will give the same, so these four terms here will give the same contribution, and when we sum up everything, you have the following result. So the same type of analysis as for the free energy, so using the Harnack property. Gives that actually this is given by, so it's the product here times the determinant of K inverse BI WJ for I and J between 1 and K, with this K inverse being this thing here. Inverse W as above. Okay? This is believable, right? So, example, if you take E1, this will be K of W1B1 times K inverse of B1 W1. If I take E1, E2, it will be K W1B1, K W2B2 times the determinant of a 2 by 2 matrix, K inverse W1B1, K inverse W2B2 minus K inverse W1B2, K inverse W2B1. And so you see that actually the natural thing to look at is the covariance of E1, E2. That will be E1, E2 minus E1, E2. And if you look at these formulas and you compute, you get the following thing. Minus K W1B1, K W2B2, K inverse W1B2, K inverse B2, oops, there's a mistake here. Wait. B2, W1. Sorry, here. Okay. I put always the B1, the B's and W's in the wrong order. So let's refocus here. These things here, they're completely fixed, okay? What we want to understand is how this thing behaves when E1 and E2 go very far away apart from each other, okay? So in this case, you see these two, basically they're fixed. They're just, okay, coefficients of the matrix corresponding to the edges E1 and E2. So these things here they're fixed. And what we want to understand really is how these things here decay when W and B grow far apart. So to understand decay of edge-edge correlations, or of covariances, we need to understand how K inverse of BW decays when the distance here goes to infinity. Okay, and if this thing decays linearly, then the covariances will decay quadratically, right? If this thing decays exponentially, this thing decays exponentially. Okay. And you see it's the same to study the decay of covariances or correlations because, again, this thing here, it's fixed. It's really these terms here that give you the decay. So in other words, we need to understand how K inverse BW plus XY behaves when, let's say, this goes to infinity. So it means we need to understand this thing here for XY growing big. And again, this thing here we know is the XY Fourier coefficient of this thing. And we need to do so for the measure, the magnetically altered measure dxby. Okay. Okay, so now it's going to be a little bit quick. Looking at this measure means, i.e., looking at P E X Z E Y W. Okay, but I think we can still have a good idea, a decent idea of what's going on. So case one, let's assume that Bx, By does not lie in the amoeba. Okay? This is equivalent to saying that P Ex, Ez, Ey, Ew is never zero for Zw on the torus. it means that this means that Q BW, so I have to evaluate everything in EX, Z, EY, W over P EX, Z, EY, W. This is analytic. And basically what happens is that if this thing is analytic, then its Fourier coefficients will decay exponentially. But now you have two subcases. So subcase A, we lie in an unbounded component. So lie in an unbounded component. Okay, so in this case, again, I mean, in this case, it's really amazing because actually at that point you have some combinatorics that come back into play. And what they do is that they use the theory of height functions, I mean Thurston stuff with height functions, to show that in this case you will have so-called frozen paths. So they use, so Kenyon and Cook of Sheffield use the, let's say, Thurston theory that we saw a little bit of height functions to show that in this case there are so-called frozen path. Sorry, I'm just going to keep this here. So what does this mean? So, i.e., path made of faces of G R2 such that each edge crossing one of these paths, crossing one of these, is present in a perfect matching with probability 0 or 1. So the kind of abstract picture would be, well, maybe I can make a not so abstract picture on the square lattice. So actually in the square lattice what will happen is that we're going to have, because they know exactly what these paths are. So it's also given by the Newton polygon and everything, but basically you're going to have, in particular you're going to have one frozen path like this, and you're going to have one frozen path like that. And each time you have an edge that crosses one of these paths, then it's present with probability 0 or 1. So you see that what will happen is that in particular if you take two edges that are in distinct connected components of the complement of this path, then they will be independent. You see? And therefore, so hence, well then this kind of explains everything. So for example, so here actually you're going to have this one, but actually you're going to have also the next one here, the next one there, and all the lifts like this. They're all going to be frozen paths. So first thing, you see that when you take two faces, a face F here, and then faces that are also another face that is intersection of these paths, then the height function on these faces, or the difference of the height functions on these two faces, will be deterministic, will be frozen, right? So you see that you are in a frozen phase. And then if you take two edges that are in different connected components, these things, then the corresponding correlations will vanish actually. Okay. So hence, so let me just say hence we are in a frozen phase. Okay. Second subcase is Bx, By lie in a bounded component. Well, so in this case, they show that there is where it's not frozen. So then it is not frozen. And then here we are good because this thing is analytic. So it is not frozen. And so the covariance decays exponentially. So first thing, this K inverse decays exponentially. This implies that by the equation I just erased that was here, these covariances also decay exponentially. And then they use this to show that then the variance, the mu variance of HF minus HF prime is bounded. And so this is not very difficult. I mean, this part here is kind of straightforward. And then the third case is really the most interesting case where they prove, well, they really spend a lot of time and it's a bit more difficult. And so I might go a little bit over, maybe by 3 to 5 minutes, because here it is really interesting. So then I forgot my numbering. So I had A, B, so case 2, yeah. Case 2, we have that Bx, By lies in the interior of the amoeba. And this is equivalent to saying that P, Ex, Z, Ey, W has a 0 in the torus. And then what they have to do is analyze the decay of this thing when we know that P has a 0. Okay? And here comes the very, very nice thing, is that in general it's very difficult to do this. But here, the Harnack property, the fact that P is actually defines Harnack curves, tells you that actually the zeros can only occur in two different ways. Either you have two conjugate zeros, or you have one real so-called node. That's the Harnack property that tells you this. So by the Harnack property, and so this is a theorem of real algebraic geometry. It's a theorem of Mikalkin. You have, if you have Harnack curve, then the zeros of this can only occur. Okay. So these zeros are either two conjugate simple zeros, or so this is the part that is a theorem, is that you can have a zero that is not a simple zero, but then it only occurs as it's a so-called or a so-called real positive node. And therefore, since they know exactly the way P vanishes, they can analyze this in a very, very precise way. So they show that in both cases, K inverse BW decays linearly as W minus B goes to infinity. So it means that the covariances will decay quadratically. And then they use this to show that that we are in the liquid phase, meaning the mu variance of HF minus HF prime is unbounded. But this part here, this small paragraph is most of the paper. No, this is a little bit exaggerated, but it's a very, very big part of the paper. So this thing here is hard. And I just want to finish with a remark. Is that with this picture, we understand the physical meaning of the Harnack property. So the Harnack property allowed us to prove that actually there is no weird decay of correlations. So you see what could have happened. Let's say that P did not define a Harnack curve. Very generally, the zeros that you get here could be completely weird. And therefore, you might have some decay of correlations, decay of K inverse, and therefore decay of correlations that would not be in these three cases. So actually, it means that the Harnack property has the following physical meaning. You have no anomalous decay of correlation. So again, the three phases covered everything, and then they translate into the three possible positions of the point with respect to the amoeba. But then it's still something to show that actually you have always the same kind of decay of correlations when you are, for example, in the amoeba. And this uses the Harnack property. Okay. That's it for today. Let me just also mention that I do not give a homework assignment this week because apparently you're kind of running late a little bit with corrections. So today you can, next time you'll be able to catch up, and I'm going to give therefore 2 more homework assignments next week and the week after. Okay. And this is the end of the first part about the Dimer model. And we have 3 weeks left. So in the next 3 weeks, I will talk about the Ising model. And you will see that the tools that we developed here can be used in a quite direct way to study the Ising model, actually. This is something that is not completely clear if you think about it a little bit. But it's the facts. So we'll have 3 classes. The first class will be basically some kind of biased introduction to the Ising model. Biased meaning I want, of course, to orient you towards the questions that I'm going to answer, because there are many, many questions for the Ising model, and they are natural that I will not address. And these questions will be addressed in the class in the 2 remaining classes. One will be about computation of the partition function, simply. How do you compute the partition function for the Ising model? And the second one will be, can one determine the critical inverse temperature of the Ising model on a biperiodic graph? And this will, of course, use something related to these stuff. Okay, have a nice week.